Video, I will be fitting non-dimensionalized data in order to form a nonlinear regression for calculating the Nusselt number based on a series of synthetic data generated for the Reynolds number and the Prandtl number. So in order to do this, first we need to import the different packages we'll need that will include the modules that will be used in this code. So first we're going to import NumPy so that we can perform calculations on arrays. Next we'll import this minimize module, which we'll be using for fitting our regression model to the randomized data that we generate. And then lastly, we'll import this random module for generating our synthetic data for the Reynolds and Prandtl number. So first we're given our constants, which are experimental values that are used in the equation for the Nusselt number. So these are given to us in the problem. Once we have these constants, we're going to need to generate a list of logarithmically spaced Reynolds numbers and Prandtl numbers. So we will have pairs of Reynolds numbers and Prandtl numbers, which we can put into the equation for the Nusselt number. So in the problem, we need 50 numbers. So we'll have n equals 50, so 50 Reynolds number and 50 Prandtl number. And so to get these numbers, we're going to use the numpy.random.randomState.choice. So inside the NumPy module, there's this inside the NumPy package, there's this random.randomState module, which will allow this line of code to pick a series of random numbers for the Reynolds number, but each time we run the code using this random state function, the same random numbers will be picked each time. So our results will be consistent each time the code is run. Next, this choice part of the code shows that we're picking a list of logarithmically spaced numbers from 10 to the negative 4th to 10 to the 10th for the Reynolds number, or 10 to the negative 1st to 10 to the 4th for the Prandtl number. And we're going to have n of these numbers, so in this case we'll be choosing 50 random numbers within this range, and using this random state, those 50 random numbers that are chosen will be the same each time we run the code. So we do this for both the Reynolds number and the Prandtl number to generate this list of logarithmically spaced and random numbers for calculating the Nusselt number. So once we have our data for the Reynolds number and the Prandtl number, we're going to calculate the Nusselt number. So this involves simply plugging in the equation for the Nusselt number that's given in the problem. But because we're trying to generate synthetic data that isn't actually 100% true to the Nusselt number equation, we're then going to take the Nusselt numbers generated by this equation and generate some synthetic data that won't fit exactly with this curve. So for this, we're going to use the NumPy random module again, but within this we're using this normal object, which in this normal object will be multiplying our true value for the Nusselt number by a series of numbers where the mean of each of these numbers will be, or the mean of this series of numbers will be 1, the standard deviation will be 0.2, and the size of this list of numbers, so how many numbers are in this list, will be the same, so it will be n equals 50. So for each data point that we generate in this line for the Nusselt number, we'll be multiplying by one of these random numbers to make our data a little bit messier than it would be if we were just calculating for the Nusselt number using this equation. So once we've generated our synthetic data, we're now going to create a model based off the data for calculating the Nusselt number. And we're going to basically optimize this model and make it more accurate using the least squares method. So to do this, we need to make a function for calculating the mean weighted square error of the model based off of the data. So we define our function, and the parameter that we used in this function is this vector v, which will have a series of values within it. So v0, v1, v2, v3, up to v6 for each of the constants that we're trying to determine to fit the model to the data. So for the sake of simplicity, rather than having each value within this v vector be referred to by its number in the array, so by v0, v1, v2, etc., within the function they'll be renamed after the constants in the equation for the Nusselt number. Once we do that, we can then generate a model for the Nusselt number where each of these constants is a part of this v vector. So each value in this vector will then be put into the Nusselt model equation. So then, once we have this model, we want to look at the difference between the model and the data. So we're going to calculate the mean weighted square error and return this for the function. So here we have numpy.mean, so the average of, here we have the difference between each value in the model and the data. So this gives us the error of the between the model and the data. We then divide that by the value, the Nusselt number based on the data, so that way we have a weighted error. And then we're going to square this so that way the negative and positive errors we will see will count equally when we're calculating our mean squared error. So once we've calculated our mean weighted square error, in order to fit the model to the data, we're then going to try to minimize this value for the mean square error. So when we use the minimize function, we need to have initial guesses for what we think these values for each of the constants in our equation will be. So our initial guesses will be these values that we were given up here, because we know, since these are the experimental values determined for the Nusselt number, they're going to be pretty similar to whatever we see in our synthetic data, even though the synthetic data has been a little messed with using this line. It'll still. So once we have our initial guess for each of the values in V, we then can use the minimize function to calculate or to optimize these values that will go within this vector. So we're minimizing our mean weighted square error using this v guess. So then this res will end up being our values for each of the constants in our equation. So then to check the accuracy of our results using the mean weighted square error, we're going to want to be able to get more precise values than what might be normally given in Python. So to do this, we're going to use the print options function and increase the precision to 6. So when we print this result, we'll get 6 decimals. And then we want to compare this to our experimental values. So if we run this code, we see that the results from our calculations from our fitted model and the experimental values for the constants are very similar. So this way we were able to accurately calculate the values for A, B, C, D, C1, C2, and C3 from our synthetic data.